So let's continue from where we left off in the last lecture, where we were looking at, we did an introduction of graphs, and then we looked at the breadth first search. And so today we'll be continuing on with the depth first search algorithm, and then we'll look at the broad topic of greedy versus dynamic programming techniques. And we won't spend too much time on dynamic programming right away. We'll reserve that for perhaps one of the future lectures when we get into dynamic programming algorithms. But we're going to be starting off looking at greedy algorithms today. And as such, we'll look at a minimum spanning tree algorithm, which you've hopefully seen before in 210, but we'll take a closer look at how the MST is a greedy algorithm and some of the properties of greedy algorithms. And then we look at, time permitting, at one algorithm which implements a greedy version of MST, which is Prim's algorithm. Okay. So this is a review of the last lecture, some slides where we looked at the breadth first search example. And we said that basically we start off by having a graph, a bunch of vertices and edges, which could be directed or undirected. And here we have a source vertex, as opposed to in the depth first search, which we'll be looking at shortly, which does not have a source vertex. And so the output is distances, which is essentially the number of edges to go from the source to that particular destination. And it will also output the tree, and that will be essentially given in the form of point of parents, right? So for every vertex, there'll be a parent which will indicate the how do you get back to the root of the tree. So this is going to be a rooted tree. And so we looked at how one would actually implement this, and we said that, well, there really is no way that I'm aware of to implement a breadth first algorithm without using a FIFO cube. And perhaps if you can figure that out, I'd be interested to find out how that can be done. And we used coloring of vertices, and this will again be used in the depth first search. So white was the undiscovered vertices. That was when they're done. And gray was something that is useful to see as you going through this. So it's not really critical for the algorithm, but gray sort of tells you where we are in search. So, and this is how we proceeded. We started off by starting with the source vertex, and we looked at its neighbors, and we sort of mentioned the location of that. So these had a distance of 1, and then as we went forward, the distances kept on increasing until we ended up with the following tree, which basically said that these are the edges of the tree, and for each vertex now we have a distance to the source. And as you can see, some of the vertices are at a distance of 2 and others at a distance of 3. And if you want to trace back to get to the root of the tree, you could simply look at the parent of each vertex, and that would give you a trail to the source. And that's where we ended as far as the breadth first search was concerned. We also did an analysis of the algorithm, and we agreed that it was essentially an order of V plus E, or you could simply say an order of E, to put it simply. And then we sort of ended on this particular slide in the depth first search. And so I had mentioned this, and hopefully you saw this earlier in whichever COM 10 course you took. At least I did this, in which we looked at why, when you're doing a depth first search, you need to use a stack versus a breadth first search, you need to use a FIFO cube. Okay. And for those of you who haven't come across this analysis before, let me just quickly take you through this. So the idea here is that we are doing a depth-first search, okay? And we start off, let's say, with the root node, and we insert that into a stack, okay, as opposed to a FIFO cube. So we insert that, and then we pop it out, we process it, and then we, after we've popped out the root node, we insert its two children, 45 and 23. The order doesn't really matter. It could be 23 or first or 45 first. It doesn't really matter. And then once you've inserted these two, then you pop 23, the top of the stack, and you now insert its two children, 9 and 15. And then you pop 9 out, and you insert its children, which are 1 and 8, okay? And then you pop 8 out, and then, well, there's 8 doesn't have any children, so then you pop out the next top of the stack, which is 1, and 1 doesn't have any children either, so you go keep going downwards in the stack. You've already popped 9 out, and then you next look at 15, and so you can see now we sort of going in the depth first analysis. We've gone all the way from 52, 23, 9, 8, 1, and after 1 we're going to 15, okay, which is part of the depth first search. And we pop out 15, we now insert its two children, which are 3 and 7 in the stack. And then we continue as we saw earlier. We keep popping out the top of the stack, and we insert its children if it has any children, and that's how it goes. And you can see that eventually you're going to end up processing 52 right at the end, okay? And everything on top of the stack has been processed. That's when 52 comes. Sorry, I was saying that wrong. That was a different order. But essentially, that's how we keep on going. And you continue on until there's nothing left in the stack. Okay. And so the last element to be the last node would be 32, not 52. Okay. So, and we had a bit of a discussion in the last lecture that could you use, if you think about recursive versus iterative algorithms to do a depth first search. And we said, well, if you're doing a stack, then recursive algorithms inherently have a call stack, okay? So if you're using a recursive algorithm to do a depth first search, then you don't have to use a separate queue or a separate stack to actually process the nodes, because the call stack does the work for you, okay? As opposed to in a breadth first search, because even if you use iterative or recursive techniques, there is no built-in FIFO cube. So you have to use an external data structure which implements a FIFO cube. And that's what we saw in the last lecture. However, in depth first search, because it's using a stack, a LIFO stack, and so if you're using recursion, that comes essentially built in for you. But however, if you for some reason didn't want to use recursion, then you still use an iterative technique. However, in that case, as somebody mentioned in the last lecture, that you could do that, but you would have to use an external data structure to implement a call stack. Okay, not a call stack, but rather simply a stack. Okay, and you could do that, but why do that if you can use recursion? Okay. So what we're going to see is a recursive technique which does the depth first search. And so this is the algorithm which is given in CLRS, and so let's take a look at that. And it does an interesting analysis in that it not only gives you the actual tree, but it also gives you timestamps. Okay, these are global timestamps, and there are two timestamps which are going to be given at the end of the algorithm. One is the discovery time of a particular node, and one is what is referred to as the finishing time. Okay, because now notice that as you're going down a particular tree, or a particular graph, then you're looking at a particular node, and then at some point you're going to finish up. Okay, so while you're looking at its children, you're not really done with that node. Okay, it's only when you are done with all its children, that's when you're essentially going to indicate the finishing time as well. Okay, why it's being done? It comes in handy if these algorithms are, of course, going to be used in other algorithms as well, and that's why it's useful to have some of these additional information once you're done. Okay, it's of course also going to give you the parent or the predecessor of V, which is essentially going to give you the path back to the root. It uses the same coloring scheme as breadth first search. So let's take a look at the algorithm. So it's going to start off by initially, of course, as before, coloring all the vertices to be white. Okay, and it's a little different from the breadth first search in that it doesn't use a particular source, okay, a particular source index to start with. It's actually going to look at all vertices, okay? And we'll see how this pans out towards the end of this algorithm, why that becomes an interesting difference between breadth first search and DFS, okay? So it's going to do this for all vertices. Essentially, this initial part is fairly straightforward, which needs to be done regardless. And so it's going to color all the vertices white, and it's going to make the parents to be initially nil. It's going to set the global timer to be 0. And for every vertex in G, it's going to now do the following. Okay, so this is very important difference between depth first search and breadth first search, in that it's actually going to, instead of using a particular source, it's going to apply this algorithm for every vertex in V. Okay, so and it's going to start off with some random vertex. Okay, and it's going to start by if its color is white. Okay, so remember all the colors are white. If its color is white, it's going to call the DFS visit function on that particular vertex. Okay, so let's take a look at an example which illustrates this. Again, this is from the book, figure 20.4. Okay, and we're going to look at every, and so this has 6 vertices. It's going to show you the status at the end of every time interval. So remember, there are time intervals, and we're going to incrementing them in ticks. Okay, so it's sort of a digital time interval. So initially, the time is set to 0, but every time we go through this DFS visit loop, we're going to increment the time by 1. When we start off, we set the timer to be 1, and we set the initial time or the discovery time of the first vertex that we're looking at to be equal to the current time. Okay, so the current time, so it's going to show the as follows. It's going to show the discovery time slash the finishing time. Okay, so the discovery time is shown as 1. And finishing time is not yet indicated because it hasn't finished. It's going to set the initial color to be gray. Okay, so as soon as it starts looking at a particular vertex, it's going to change its color from white to gray. All right, and then for each vertex in its adjacency. All right, so the adjacency of U are V and X. So for each one of those vertices, it's going to explore that particular edge. Okay. So when it starts off, it's going to check whether that particular vertex has already been explored or not. And that's going to be indicated by the color. So if the color is white, it means that it needs to explore that particular vertex. It's going to set the parent to be itself, okay, naturally, because it's been explored from U. So V's parent is going to be U. And then it's going to do the recursive part. Okay, so we already saw that this is going to be a recursive algorithm. So this is where the recursion comes in. And now it's going to do a recursion on the first adjacent vertex that it picked, okay, which could be any one of those. It could be V or X. but it's not going to explore X right now. It's going to now explore V in a recursive manner. Okay, so you can sort of see that now we're going to go in a particular direction of V, and then we're going to probably explore Y and probably X before we're going to come back and explore the other vertices which were adjacent to U. Okay, so now we're going to go through this recursion over here. We're not going to look at setting up the finishing time until we're done with exploring the entire depth of that particular vertex adjacent. Okay. So here are some more as we continue on. So once we're done with the first time, we now this time has become equal to 2. Okay. That's been incremented over here. We set the discovery time of the vertex to be 2. We change its color to be gray. And then for each vertex in the adjacency of V, we're going to now explore that, okay, if it is white. So if this guy, Y is white, so we're going to set its parent to be V, okay? And then we're going to do a recursive exploration of Y now, okay? So you can sort of see where we're going. We also are going to define the following types of edges. So a T is going to be essentially a tree edge, okay, which basically means that it becomes part of the depth first search tree, okay? But you may have also some back edges and some forward edges and some cross edges, and we'll take a look at what those mean as we go forward. So let's keep going on with this particular example. So we're down to now T is equal to, this was T, C is equal to 2, now T is equal to 3, okay? So we now are doing the third recursion. We've incremented the time to be 3. We set the discovery time over here to be 3. Color, it's the vertex to be gray. And then again, each vertex in its adjacency, we're going to explore that. And you can see how we're progressing forward. Okay, so now the next time we're going to explore this particular vertex, we're going to set the time to be 4. The discovery time. And now something interesting happens. It looks at its adjacencies, and it sees an adjacent vertex, which is V over here. And it realizes that it is not white in color, okay? So it's not going to explore that, okay? And so this particular vertex, just for information purposes, is going to be labeled as a back edge. And nothing is essentially going to be done, but it's just an indication that it's a back edge, okay? And so it's not going to increment the time until actually the recursive call. So it's going to continue on and look at other adjacencies, so there are none. And so that's when it's going to say, well, I'm done with the adjacencies of node X, okay? And that's where it's going to come out of this particular loop, and it's going to increment the time, and it's going to set the finishing time of that particular vertex to be the new time, which is now 5. Okay, so now you see that the start and finish time of vertex X is set to be, it was initially discovered at time 4, and then it was finished at time 5. Okay. And so we continue on with that process. We're done with this particular node. And so we're going to recursively go back. And then we're going to say, well, that was the end of all the vertices which are adjacent to vertex Y. And so we're going to set the finishing time of Y to be 6. And similarly, the finishing time of V to be 7. And then we come over here, okay? And we get back to U. And we say, well, there was an unexplored edge, okay? We look at that unexplored adjacent edge to U, and we say, well, look, let's take a look at the color of the vertex, which was adjacent to it, and it's not white, okay? And so this is going to be labeled as a forward edge, okay, as opposed to a back edge, sort of showing you in the picture that, but it doesn't really have any significance in the actual, okay? So this is labeled as a forward edge, and so there are no other vertices which are adjacent to U now, and so it ends. The finishing time is not set to be T is going to be 8 over here, so it sets the finishing time. Okay. So are we done with the algorithm? So we started off with a particular vertex randomly that happened to be U. We explored all of its adjacencies, and we essentially done with all of that. And now think back to the start of the algorithm. What should happen next? Now we done with one particular vertex, and that is the difference between breadth first search and depth first search. In breadth first search, we started off with a particular vertex, right? In depth first search, and I'll just show you the algorithm again. We said that for each vertex, U and V, we're going to conduct the visit of that particular vertex. So are we done with this entire loop? When we're done, let's say over here, once we're done with this particular set of vertices, do you think we're done? If not, what are we going to be doing next? So just look at the algorithm and yeah. Exactly, right. So you look at the next vertex, let's say you look at V, and you realize that is it white? It's not white anymore. So you keep on going. Let's say you get to W, all right? And you realize that W is white. And so now we're going to repeat the entire process with this new vertex, which was W. Now notice that this is a different example, and it is a directed graph. Okay, so we're giving you there's some examples of directed versus undirected graphs. So yeah, okay. Here's what's going to happen with W. You start off exploring W again, just like before. You look at its adjacencies, and you look at the first adjacent vertex, which happens to be node Y. Okay, it's not white, and so it's indicated not as we're going to indicate this not as a forward index, a forward edge. Rather, it's going to be considered as a crossover edge. Okay, so these are cross edges. Okay, and why is that? You can hopefully see that the reason why it's a cross edge is because now you are essentially creating multiple trees in your graph. Okay, this is one tree, which is a depth first search tree. Okay, which has these edges. And here is another tree being formed. And so this is saying that W is now, it has a child, it has an adjacent vertex, but it is in the other tree, okay? But it isn't white, so we're not going to use that particular edge, okay? So we're going to just label that as a cross edge. And then it's going to look at another adjacent vertex, and Z, and this happens to be white. And so we're going to do the time stamping, and it also has a self loop. Okay, so in directed graphs, remember you can have self loops. So it's going to look like self, and it's going to call that a back edge. Okay, because pointing to a vertex which has already been explored. And so these are the timings that are going to be noted, and eventually the recursion is going to end back at vertex W, and it's going to have a finishing time of 12. Okay, so that's essentially the depth first search algorithm as given in the book, and it's an interesting algorithm. And the first question is, can we analyze it? Okay, and we did sort of a brief analysis of the breadth first search. So let's do a quick analysis, not a very rigorous analysis, but sort of an intuitive analysis of the depth first search as well. So any thoughts on that? Do you think it's going to be about the same as the breadth first search, or is it going to be a different time complexity as compared to the BFS? Any thoughts? And think back at the actual algorithm. Just take a look at the algorithm and try to see what do you think is the complexity. Is it going to be order of vertices? Is it going to be order of edges? Is it going to be some product of the two, some sum of the two? And if so, what? Okay, so let's take a look at this algorithm. So you can clearly divide it up into two parts. So without considering the recursion part, let's just take a look at lines without the actual visit. Okay, so if you think about the initialization component, how much time is that going to take? And that's kind of similar to the initialization component of the breadth first search. Okay, so how long do you think that's going to take? It shouldn't be too hard. Is it proportional to V or is it proportional to E? Basic question. Yeah. Big O of E, V, yeah. So you can essentially see that we're looking at all the vertices. Okay. So this part is essentially going to be proportional to V. Okay. And then if you look at the recursive part, if you think of the recursive part, what do you think is the complexity of the recursive part? Right. Now, what are we doing in the recursion? Are we looking at the vertices? Are we also looking at the edges? And think about if it's a dense graph versus a sparse graph, what is the difference going to be? So think about an extremely sparse graph first. Okay. What's the complexity of the recursive part going to be? So again, think about this. Let's say it's a very sparse graph, or whichever way you prefer. You can think of it as a very dense graph or a sparse graph, and try to come up with, sort of an intuitive response as to what the complexity of this algorithm is. Is it really different from the breadth first search in terms of complexity? Any thoughts? So we're looking at the adjacencies, remember? Okay, so for each vertex, we start with a particular vertex, we look at all its adjacencies. So what does that indicate? Is it simply going to be proportional to V, or it's going to be proportional to E? Yeah. E, clearly, because now it's exploring all the edges. So if it's a very dense graph, then you could have the number of edges could be as high as V for every vertex. And because looking at every vertex, for every vertex, there could be another vertex which is adjacent to it. So it could actually be proportional to as high as V squared. Okay. So if you think about this, essentially, you can eventually see that it's essentially proportional to, very similar to breadth first search, that's going to be proportional. It's also going to be proportional to the number of edges. Okay, and for a dense graph, E would essentially be order of V squared. Okay, so this was a really quick look at depth first search and doing a really quick analysis. Okay, so that's a quick summary, but that's something that we've already seen. Okay, so now let's take a look at something which starts becoming interesting as far as this course is concerned. Okay, so I mentioned that there is this algorithm which is considered, you might have heard about this, greedy algorithms versus dynamic programming. Okay, has anybody heard of these algorithms before, and what do you know of them? Broadly speaking, what class of problems do they try to address? Has anybody heard of them, first of all? Some of you have you covered this in any one of the courses? Was it covered in any course at UNC? Or no, on your own, you've come across it. So what's your general understanding? I mean, what categories of problems do they address? Yeah. Okay. So can I get your names again? Sorry, I keep forgetting. Thomas. Okay. So Thomas's suggestion is that the greedy algorithm is an approximate algorithm, and it's an approximate algorithm which will try to guess, an optimal, the perfect solution. Is that basically what you said? It's an approximate solution. Okay. So it sort of gets you close to the destination, perhaps, or it's 89% good, you might say. It may not be the perfect solution, but it's a good solution. Anybody else? Okay. Okay, very good. So you summarized it quite well. So you use the word optimal. Okay, so what does that indicate to you? Both of these are essentially optimization problems. Okay, so essentially you're trying to find a solution. Trying to find an optimal solution. Okay, so whenever you think of any problem which requires optimization, okay, that's when these two classes of problems come in. Okay, and some of the problems that we look at in graphs, for example, as I said, the minimum spanning tree, when you use the word minimum, that essentially indicates that it's trying to optimize. Okay, it's trying to optimize the minimum, the overall weight, for example. So it's looking for some kind of an optimization. And from Tomas's suggestion that a greedy algorithm may not, from your estimate, from where you coming from, you think that greedy algorithms may not get you the perfect optimal point, but they might get you something close to the optimal point. Did you agree to that, Kyle? Okay, so it's not very clear from both of your comments whether a greedy algorithm can be an optimal solution or not. All right, so you think it might be getting close to an optimal solution, and from what I understand, you're saying that there are certain properties, and if those properties are satisfied, then it may be a globally optimal solution. Okay, yeah. In the, sorry, general? Yeah. So essentially what you're pointing out is that there could be some category of problems where a greedy algorithm may not give you a globally optimal solution. Okay, so if you think about, you're trying to, you have some kind of a terrain, and you try to find out the optimal solution. And if you look at this particular terrain, let's assume this is a mountain peak, okay, set of mountain peaks, and you start off at one particular spot, and you know that the global solution, just by looking at it, the global optimal solution, the maximum peak is at this particular point, right? But if you're starting off in one of these throws, okay, you're starting at one of these points, then a greedy algorithm may perhaps just get you a local optimum, okay? And it may get stuck in a local optimum, and it may not be able to get you to the global optimum, okay? So, for example, you could be starting over here, and it might just find you a local optimum, okay? If you happen to start over here, the local optimum would actually be the global optimum, okay? So it also depends on where you start off, but a greedy algorithm perhaps does not guarantee a globally optimal solution, okay? However, I think as Kyle mentioned, is that there could be some scenarios where for some class of problems, you could use a greedy algorithm, and it could confirm that for that particular class of problems, a greedy algorithm will provide you a globally optimal solution. Okay, so that's not always going to be true. It's going to be true for class of problems. Okay, and you might ask, well, how do we know a priori whether a particular category of problem a greedy approach will give you an optimal solution or not? That's a difficult question a priori to answer. Okay, you don't generally know if you look at a particular problem whether a greedy approach will give you the globally optimal solution. However, what we do know is that dynamic programming will give you a globally optimal solution. Okay, so dynamic programming is a little bit more intensive. It's not as fast, but you look at perhaps all the possible solutions and will guarantee that you get a global optimal. Okay, and so essentially, what you can say from what Thomas said is that if you look at generally at a class of different problems, then for maybe a whole bunch of types of problems, the greedy algorithm, as you said, may give you maybe close to the global solution. It may not guarantee it. Okay, but for some class of problems, it will guarantee it. And so the class of problems that we're going to initially look at, the first one that we're going to look at is the minimum spanning tree. Okay, and that somehow has been shown that a greedy algorithm, in fact, will give you a global optimal solution. Okay, so that's why it's interesting to look at MST and use greedy algorithms. And then once we're comfortable with applying a greedy algorithm and understanding what is a greedy algorithm and seeing how it is applied in this particular case successfully, then we can sort of see other algorithms where maybe a dynamic programming technique would be better. Okay. So I think Kyle also mentioned this, that there are two aspects to your algorithm, okay, which need to be looked at before we can, first of all, even decide whether you can use a greedy algorithm or a dynamic programming algorithm, okay? And these two aspects are something called an optimal substructure, okay? And then something called an overlapping subproblems, all right? And so just to start off with, the optimal substructure is required for both of these algorithms. And this in particular is the overlapping subproblems is in particular required for the dynamic programming technique. Okay. So, but we'll take a look at both of these aspects in a few minutes. And one of the things that I've already mentioned is that the greedy technique makes a local optimal choice. Okay, so as you can imagine, if you're over here and you're trying to find a solution using a greedy technique and you're over here, it's going to look at the local situation and say, well, I'm going to make a decision which is locally optimal. Okay, and if you're right on this particular edge of a mountain, you can clearly see that the local optimum will say that I need to go up this mountain. All right, and I'm going to go to the right. However, we actually know just by looking at this terrain, the actual optimal solution is by going to the left. All right, so the greedy algorithm is going to make a local optimal decision, okay, which may, as you said, not necessarily give you a global optimal. So it's a locally optimal choice, and the hope is there that it will give you a globally optimal solution, but again, it's not guaranteed for all classes of problems. So what do we mean by an optimal substructure? So those of you who've come across this before, again, need your help to define. What do we mean by an optimal substructure? Okay, so I said that it requires an optimal substructure. So don't expect you to know this, but somebody can know this. You can verify your concept, and we can see how that sizes up. Okay, yeah, that's a reasonable answer. Okay, so let me explain this. So let's take a look at a different problem, which is a shortest path, which is a little easier to understand. So you hopefully have come across shortest path problems in 210 as well. So in a shortest path algorithm, we basically say, well, let's say we have a particular source and we have a particular destination. Okay, So these could be roads, all right, or these could be plane hops and so on. And let's assume that there's some distance between every pair of adjacent vertices. So A and B, the distance is 10. A to C is the distance is 3. That could be, for example, hours commuting versus 3 hours commuting, or it could be $10 or $10,000 or something in terms of cost. It could be time or price, what have you. Okay, and so there are these different costs associated with every edge. Okay, so this is a graph which has not all the edges are present. Okay, so for example, A does not have an edge to E, but it does have adjacencies to B and C. So when you say that this particular problem, which is the shortest path problem, has an optimal substructure, what do we mean by that? Well, what we mean is that if we somehow were able to figure out what the shortest path is, and you can sort of look at it and you can say, well, the shortest path, and just by looking at it, we can say that this is 10 plus 5 plus 15 plus 1, and that comes out to be 31. If I go on this particular direction, the cost seems to be lower than 10, okay? But this cost over here is much higher, okay? So the weight over here is much higher. So going this way would go take 23 to get from A to D versus this would take 15. So clearly ABD is shorter than ACD, okay? And similarly, DEG is shorter than going through DFG, which will be 27 versus 16, okay? So hopefully you can see that just from intuition that ABDEG is the shortest path, which I've shown here in the tan color, okay? But what do you mean by an optimal substructure? By optimal substructure, we mean that if you take the particular route and ABDEG is the optimal route, then any sub-problem, any sub-part of it or sub-route, for example, ABD, okay? So if you take a look at ABD, then this is also the optimal path from A to D, okay? And similarly, if DEG or any sub-route is on the optimal path, then it is also the optimal path for that sub-problem, okay? So in other words, DEG is also the optimal path from D to G, okay? Similarly, B, going from B to G, the optimal path is BDEG, which is part of the original path, okay? So hopefully you can see that in the shortest path, it does have the optimal substructure property. Okay. Now, in order to understand that better, it's really useful to see where this is not true. Okay. So where would this not be true? Can you think of an example where, let's say, somewhat similar to this, or you can think of a completely different example, but can you think of an example, a contrary example, which says that the optimal substructure property is not present? Can you think of a particular problem where that is not present? Where you can't just so think of it as, you can think of it in the same domain to make it simple. When would going through this particular route and you take any sub part of it, the total may not be equal to the sum of its parts, in other words. When do you think that might be the case? That the total is not just the sum of its parts. So think of a ticketing example, okay, airlines. If you're going from A through G, and Google Travel, for example, tells you that the best way to go from A through G is to make 1, 2, 3, 4 hops. And that somehow gives you the cheapest ticket to go from A to G. Okay, cheapest ticket. Now, would that necessarily imply that if you want to simply go from A to D, would this route be the optimal route? Or could ACD be optimal in that case? Think of airline ticketing. In your experience, would airline ticketing be an example where it has optimal substructure, or it's a contrary example? And if so, why? I'm sure all of you have traveled and have had these issues of, going from 2 destinations, and sometimes the costing structure of airline tickets, is it always necessarily a sum? Is the cost simply a sum of its parts? It's not, right? I mean, even if you think about a round trip ticket, so if you're going to a particular destination, you're coming back, if you bought 2 separate tickets, going and then coming back, would that necessarily be just the total cost for round trip ticket? Would that simply be the sum of the 2 parts? Really not, right? Why is that? Because they take, that's how sales works, marketing. That's how marketing works. You give discounts. So if you want to give especially a discount, you may say that, well, if you're going from A, if you're going through this particular multi-hop route, then I'm going to give you a special discount. It's up to the airlines. But that doesn't necessarily mean that if you're just going from A to D, then this particular route is going to be the cheapest. Okay, it's possible that this particular route is actually cheaper. Okay, that's how sales works. Okay, so this is an example where the optimal substructure may not hold. All right, because you have bulk discounts and so on. So that was one example. The other issue that I think Carl mentioned is the issue of overlapping subproblems. Okay, now what do we understand from overlapping subproblems? Somebody else, perhaps. And so in you sort of had an indication of this. Can you recall any one of the homework assignments that you did where you sort of were indicated that the problem may have an overlapping subproblems? Think back, you've only done 3 assignments. So it's one of those 3. Which one was it? Did it have an overlapping subproblems? Yeah, it does. Yeah. Yeah. So we said that you could go either this way or this way. Okay. You could go this way and this way. Okay. But if you're following this particular route, you could have also followed this particular route and you're ending up in the same location. Okay. So that is an example of overlapping subproblems. Okay. Any other examples that we can think of? So let's take a look at something that I'm sure you've come across before, Fibonacci series, and you're trying to do it in a recursive way. Okay, so if you try to solve f of 5 in the recursive way, you say, well, I'm going to calculate f of 4, f of 4, f3, f2, and you can see that 2, 1, and 0, and so you can see that there's a whole bunch of overlapping subproblems. Okay. F1 is over here, it's over here as well, over here, and then F2 is appearing here, and so on. Okay, so if you're trying to do a recursive solution to the Fibonacci series, it's a terrible way of doing it, right? Because you're going to be taking an extremely long time because you're going to be solving sums which are overlapping over and over and over again. Okay, so you don't want to do that. And so dynamic programming does allow you to solve this in a better way, but we'll take a look at that later on. Okay, but so far you can see that you have overlapping sub-problems in some categories of problems. So now let's talk about minimum spanning tree. Okay, so this is something that, again, you've hopefully have come across before, but essentially the following is a definition of the problem. Let's say that you want to connect a set of nodes by a network of minimal total length. Okay, you have a set of nodes, and each one of those edges has a weight, and you want to have the minimum weight which connects all of them. All right. And the kinds of problems that you can think of are, for example, communication networks, circuit design. So we discussed an example. For example, if you have a city and a cable network is trying to lay cables to connect all the homes, okay, and each one of those distances are different. So you just want to have you want to minimize the total cost of the cable. So you want to have some interconnection which connects all the homes, and it also wants to ensure that the cost is minimal. And this comes in extremely important, for example, in circuit design. If you're thinking about your motherboard and all the wires which are interconnecting the pins, that becomes very relevant over there. Okay. So before we go ahead, let's take a look at some definitions, and this should hopefully be a review for most of you. So can somebody tell me the difference again between a tree and a forest, and what is a tree? How would you define? So here you have a graph. Okay, it consists of a bunch of vertices and a bunch of edges. So when I say a tree, what do I mean? Can you define it in brief? What is a tree? Kind of obvious, but just to say the obvious. And how would it be different from a forest? You have come across this before, right? We did do it in 210, maybe very quickly. So, person who's shaking their head, you didn't do this at all in the 210. I presume you didn't take it with me, right? So you didn't do this at all in 210. I can't believe that. Okay, go ahead. No, I'm sure that all of you have not taken it with me, but in the 210 that you did take, so the 210 that you did take, right? Did you cover graphs? Now you're remembering, okay? So I'm sure that you covered trees versus forests, okay? But I'm not going to spend too much time on this because I know it's a revision. So a tree is acyclic, first of all, and we covered this in the last lecture. It's also connected. Okay, versus a forest is basically a bunch of trees which are not connected. Okay, so as you can see that for the same graph, you could have different trees. Okay, so this is one tree, this is another tree, this is yet a third tree. This particular tree is a single island. Okay, but this entire set of trees would be called a forest. Okay, but it's important to understand that tree is acyclic. Okay, shouldn't have any cycles, so you shouldn't have any connections which are forming cycles, and it should be connected. Okay, so these two are not a single tree. These are two separate trees, not a single tree. Okay, so tree versus forest. Now, rooted versus a free tree. Has anybody come across this before? So you've come across. In 210, you've come across rooted trees. So mostly when you talk about trees, you saw binary search BSTs, you saw heaps, okay? And they always had a root, okay? So we started off with a root at the top, but do all trees have a root? No. So all trees don't necessarily have to have a root, okay? So you could have a tree which is referred to as an unrooted tree, and that unrooted tree is called a free tree. Okay, so this particular tree that I've shown over here, because there is no specific designated root, so it's called a free tree. Okay, and if you want to convert a rooted tree out of this, for example, what you could say is that I use the vertex D as a root. okay, then that particular tree becomes a rooted tree, okay? And so another example is that you could use the vertex E as the root, and so now it forms another rooted tree, okay? And then when it does become a rooted tree, it also essentially has directions in all the vertices. Now, I didn't mention that a tree, whether it has directions or non-directions, okay? But it could have directions, the edges could have directions, or the directions maybe, it could be directionless, okay? So a tree starting off with may not have any directions, but if it is rooted, then clearly you can identify the direction. And you could say, well, the direction of every node is somehow related to the direction to the root, okay? And remember, it's acyclic, so there is only one path to get to the root, okay? So between any two vertices, there's only one path in a tree, and that's called the simple path, okay? There's only one path. And so this becomes a directed acyclic graph, a DAG, okay? Why is it a DAG? Because you could define the directions. You could define the directions in different ways. I mean, I'm defining the directions in the sense of, and then you can define parents and children as well, okay? Because if this is rooted at D, then you can think of D as the overall hierarchical parent, okay? And everything, every vertex which is away from it is its children. Okay, so in this case, it has 3 children, okay, and the children of its children become its grandchildren, and so you have this relationship between parent versus child, and so in that case, this tree becomes a directed tree, okay? And because it's acyclic, it's clearly a directed acyclic graph. Okay, so that's a difference between a rooted tree versus a free tree. And so far, I think in 2, we never came across a free tree, and so this may be the first time you're coming across a free tree, okay? But that becomes important in a minimum spanning tree algorithm. Let me introduce one more concept before we go forward, and this is the concept of an induced subgraph. Anybody come across this term before? Induced subgraphs in any of the other courses? No? Okay. So let me introduce what that means. So let's say that you have a graph, VE, okay? Let me take a set of vertices, which is a subset of the vertices of the graph, okay? So for example, if I take E, F, and G, E, F, and G as V1, okay? So this is a subset of the set of vertices. Okay. Now, my question is, what would be the induced subgraph of V1 based on V1? Okay. So given that V1 is a subset of the vertices, what would be the induced subgraph G1, which is based on V1? Now, I haven't told you what E1 is, which is a set of edges of that induced subgraph, but think about what could it be from an intuitive understanding of what maybe an induced subgraph could be, okay? So clearly it only consists of the vertices V1, all right? So the induced subgraph is clearly only going to have E, F, and G, right? But then the question is, which vertices should we include in that induced? And what's your guess? Should we include these edges which are outside of the vertex? Probably not, okay? So it's a very simple term, it's a very simple concept, but it's important, so that's why it needs to be addressed. And so an induced subgraph simply says that we're only going to look at the vertices which are within that set of vertices, okay? We're only going to look at those edges which are within the set of vertices. So we're only going to, so this will be the induced subgraph of E, F, and G. Okay, fairly straightforward. So an induced subgraph of A, B, D, and E would be A, B, D, and E. So we'd only look at the edges which are within that. So the definition would become that E1, the edges of the induced subgraph, would be all the edges such that both U and V are within the set of V1 vertices. Okay, so both U and V are within. So we'll take every edge in the original graph. We're not going to create new edges. For example, we're not going to have this particular edge because it wasn't there in the original graph. We're only going to look at those edges which were there in the original graph and in which both of these vertices are in the subset of vertices. Okay, so this is V1 example, this is V2 example. So it's a simple concept, but it can become a bottleneck if you don't understand what this is. So those are the three concepts: a rooted versus free tree, an induced subgraph, and tree versus forest. Okay, so hopefully you've got that. So if you understood that, now let's formally define the definition of a minimum spanning tree. So given a connected, undirected graph, okay, so we're only going to be limiting ourselves to undirected graphs. Okay. Given this with vertices and edges, and also edge weights. Okay, so as I said, obviously, if you're looking at a minimum spanning tree, it must have weights for each edge, just like shown in the shortest path example. So those weights are given by W, U, comma V. Okay, a spanning tree is an acyclic subset of edges T within E that connects all the vertices together. Okay, so that's important. So when you say a spanning tree, it has to connect all of the vertices. So it's a tree. So just like your example, if you look at this, well, this was a forest. All of these are trees, but you can clearly see that that in this case you may have examples. That was a good example, but we look at other examples where you could have a tree which is not connecting all the vertices. Okay, just like in the problem that looking at connecting all the homes, you obviously don't want to leave out some homes disconnected with a cable. So a spanning tree needs to connect all of these homes or all of these vertices. Okay, and it has to be acyclic. Why? Because you're trying to minimize the cost. What advantage would a cycle have? Right. So think about connecting your homes with the cable, and if you had a cycle somewhere, then clearly one of the edges in the cycle can be removed, and to minimize the total cost. Okay. So it doesn't make sense to have cycles. So it's always going to be acyclic. Okay. The cost of the spanning tree is simply going to be the sum of the edge weights. Okay. So we're simply saying that for every edge in that tree, we're going to sum up all of the edge weights, and that's going to be called the cost of that spanning tree. Okay. And again, similarly, since this is an optimization problem, we're going to now look at the minimum spanning tree. Okay, so you could have multiple, you could have an unlimited number of spanning trees in a particular graph, not unlimited, but a very large number, of course. But we're now going to look for the minimum spanning tree, in other words, which has the minimum cost. Okay. So now let's take a look at this particular graph and try to see, can we just from intuition figure out what would be the minimum spanning tree? Okay. And this is where again, to be able to sort of use our own intuition to see, well, what should be, which edges would you want to have in the minimum spanning tree? And you may use an algorithm which you've already studied in the past, but I'll leave it up to you. Okay. So any volunteers? Anybody would like to volunteer? Jane? A to C, okay. Good start, yeah. A to B, B to D, okay. Sorry. D to F. D to E and E to G, okay. That looks pretty good. So now I want to understand your thought process. How did you figure that out? What were we looking at? Okay, so you sort of started with one end. You started from the left side A, and you said, well, A to C is clearly very small weight as compared to 30 and 10. Is that how you did it? Okay, so did you, when you think about A, did you look at 3, 30, and 10? And you compared those three and you said, well, 3 seems to be the least cost edge of A, okay? And so you started off by connecting that. And then you looked at, well, here was a little bit of a non-intuition. I'm not sure how you selected A to B. How did you select A to B? So you're looking at now B, and you need to connect that to A and C. A and C are already connected. So you were trying to think, well, you could go this way, all right? You could go this way, all right? Or you could go directly, right? And is that how you're thinking? And then you said, well, clearly there's a 30 over here, so that couldn't be good. And there is a 21 over here, that couldn't be good. So this seems to be the lowest cost. Okay, so that's how you decided that B to D would be connected. Okay, so that's you know, intuitively you're thinking along the right lines, but we need to, of course, convert that into an algorithm. Okay, but that's how essentially one would think about it. Is that you take a particular vertex and you say, well, how do you connect it to other vertices? And Jane initially said, well, let's look at the least cost edge which connects it to other neighbors. So that's the first thought, okay? But then it became more tricky because now you have multiple, you have multiple routes, and it's not clear that this B is actually has a least cost edge to D, which is 5, and 10 is actually a higher cost edge for B. So if you just focus on B, then it's not clear how should you connect B through to A, okay? And so now you're going a little bit further because you have a global picture. You can see, well, B2, and you're going multiple steps now. You're not making a local decision, you're making a multi-hop decision, okay? But if you think about a greedy algorithm, we know that a greedy algorithm is probably going to make a local decision, right? It's going to find a locally optimal. So let's just think about, what do you think a greedy algorithm would want to do, okay? So, so let's just remove some of this and think about, if you're starting from A, what do you think a greedy algorithm would want to do? Sort of similar to what Jane suggested, but let's expand that thought. What do you think a greedy algorithm would do? And that's exactly what Jane did. What did you do? You picked the least cost edge, okay? You pick the least cost edge and you said, well, let's start with that, okay? So that seems to be a locally optimal solution, okay? But then this 10 wasn't really locally optimal, okay? Because you're going with 5 and 10 and 21, and 5 could have been locally optimal. So you could have said, well, let's connect B to D first, okay? But then you have a problem that you have this particular edge and you have this particular edge, and now is that a single tree? If you did decide to use locally optimal solution, then let's say you connected A and C, okay, and then you looked at B and you said, well, let's connect B and D because it seems to be locally optimal, okay. And now, is that a tree? Is that a forest? So it's a forest, right? Because now you have one tree over here, okay, and you have another tree over here, okay. So that sort of going in a different direction, and maybe you could come up with an algorithm which could do that. And if some of you remember 210, there was an algorithm which does that. Okay. But we're going to look at slightly, there are a couple of algorithms which can solve MST. And one of them is slightly better than the other. So we're going to look at one algorithm, and that's a little different from what we just did, okay, or what this is showing. So here's the MST, which happens to be exactly what was suggested, okay? That's good to know. And the cost would be the sum of all the weights. So if you just sum up all of these weights in the tree, that would be the cost. And hopefully you can see that that is, in fact, the minimum cost, okay? So a quick question, is a minimum spanning tree always unique? Can you have different MSTs in the same graph? And what would determine whether it's unique or not? So in this graph, I know it's a little complicated to think about, but I mean, think about something really simple. Let's say you have 4 vertices and all of the edges have a weight of 1, okay? So could you come up with, is there a single MST solution to that? Clearly not, right? Because you could come up with a solution which connects these edges, okay? You would come up with another solution which connects these edges, all right? And they would all have the same weight, okay? The weight of this one would be 3, the weight of this one would be 3, but there would be different minimum spanning trees, because in this case you have going this way, and in this case you have going this way, okay? So you can clearly see that the minimum spanning tree, it doesn't necessarily have to be unique, and you hopefully got an idea that especially when edges have the same weight, then you could have a problem, okay? So here is an example from the book, and you can see that it is not necessarily unique. So can you think of why it's not unique, and how could you think of another spanning tree which would have the same weight? So just by looking at it, can you come up with another spanning tree with a minimum spanning tree which has exactly the same weight? And you can guess, you have to look at what edges which have the same weight, right? That's where, you know, if you swap those around. So what about if we swap 7 and this 7? Would that form a minimum spanning tree? No, why not? Because now you can see that you're forming a circle, right? So that's not a good solution. So any other thought? Which other edge could we swap to? Again, yeah, Raj? Yeah, so you could disconnect this, and this has the same weight, and so clearly the minimum spanning tree cost would be the same for both of them.